Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the fourth part of Chapter 9, Self-Induction. At the end of this chapter, the student will be able to give the expression of the magnetic energy stored in a coil, interpret the spark produced when switching off a circuit. Now let's remember from the previous video, the differential equation during the growth of the current is di over dt plus r over Li equal E over L. The solution of the differential equation di over dt plus r over Li equal E over L is I equal I maximum into 1 minus exponential minus t over tau. Differential equation during the decay of the current is di over dt plus r over Li equal to 0. The solution of the differential equation di over dt plus r over Li equal to 0 is I equal I maximum e to the power minus t over tau, and the time constant tau is the time needed by the current to reach 63% of its maximum value during its growth, and the unit of tau is second. Now, in order to explain the magnetic energy stored in the coil, let's first talk about the power distribution in a coil. The potential difference across a coil oriented positively from A to B is equal to UAB equal Ri plus L di over dt. Now multiply both sides by I, we obtain I times UAB equal Ri times I plus Li di over dt. So I times UAB equal Ri square plus Li di over dt. The previous equation can be written in the form P total, since as we know P the power is equal to I times U, so P total equal the P lost plus P magnetic, where P total equal to I times UAB is the total power received by the coil during the growth of the current, and the unit of power is Watt. P lost equal to Ri square is the power lost by Joule's effect in the resistor of the coil, and P magnetic equal to Li di over dt is the magnetic power associated with the self-induction in the coil. Now, the expression of the instantaneous power is P equal derivative of energy with respect to time. So, since P equal dW over dt, dW equal P times dt. Now, integration both sides with respect to time, we obtain W equal integral Li di over dt, which is the P magnetic, times dt. We cancel dt with dt. We obtain W equal integral Li di. Since L is constant and the integral of I di is I squared over 2, we will obtain half Li squared plus constant. Now, as we know, the constant is determined using the initial conditions. W equal half Li squared plus constant. So at t equals 0, I equal to 0, and the energy was equal to 0. So when we replace I equals 0 and W equals 0, we will obtain constant equals 0. So the expression of the magnetic energy stored in a coil is given by W equal half Li squared. Of course, the unit of energy is Joule, L in Henry, and I in Ampere. Now, during the growth of the current, we know that I equal I maximum into 1 minus exponential to the power minus t over tau. So W will be equal to half L I maximum squared into 1 minus exponential minus t over tau squared will be equal to W maximum 1 minus exponential minus t over tau squared, where W maximum is equal to half L I maximum squared. From this expression, we can deduce that W is increasing, and hence the coil is storing energy. It acts in this case as a receiver. Now, at the end of growth, I will be equal to I maximum, and so energy will be equal to half Li maximum square, which is W maximum. As we see in this figure, W starts from 0, it increases as I increases, and at the end, the value of energy will reach a maximum value called W maximum, which is equal to half L I maximum squared. Now, during the decay of the current, I equal I maximum e to the power minus t over tau. So, W equal half L I maximum squared into e to the power minus t over tau squared, which is equal to W maximum e to the power minus t over tau squared. So W decreases, and hence the coil is supplying energy to the circuit. In this case, the coil acts as a generator. At the beginning of the decay, the current was equal to I maximum, and the energy stored in the coil was maximum. And at the end of the decay, of course, the current will be zero, and so the energy. As we see in the figure, the energy starts from a value W maximum and decreases till it reaches 0 after 5 tau. Now let's solve application 6. In the adjacent circuit, E equal 10 volt, R equal 1 ohm, R prime, the resistance in the coil, is equal to 4 ohm, and L, the inductance of the coil, is 1.2 Henry. In the steady state, calculate the current and the potential difference across the coil. At the steady state, we know that I is constant and is equal to E over R total. So I equal E over R plus R prime equal 2 ampere. At the steady state, in this case, of course, the coil acts as a resistor of resistance R prime, since the current is constant and di over dt equal to 0. So the voltage of the coil will be equal to R prime I maximum equal 2 times 4 equal 8 volt. Now we open the switch case suddenly, calculate the self-induced EMF in the coil, assuming that the current decays linearly with time and becomes 0 in a time of 4.8 milliseconds. Do you notice that a spark at the switch? And justify. Since the current is decreasing linearly with time, so di over dt will be the slope of this line, and it will be equal to minus 2 over 4.8 times 10 to the power minus 3. Minus 2 here, since we have the current was 2 ampere and then it becomes 0 ampere. So 0 minus 2 over delta t, which is equal to 4.8 times 10 to the power minus 3. Of course, times 10 to the power minus 3 is the converting from millisecond to second. So di over dt will be equal to minus 2 over 4.8 times 10 to the power minus 3. And since E equal to minus L di over dt, we will have E equal minus 1.2 times minus 2 over 4.8 times 10 to the power minus 3, which will be equal to 500 volts. Now, using the law of addition of voltages, UG, which is the voltage across the generator, equal to U coil plus UR plus UK, which is the voltage across the switch. When the switch is opened, the current will be 0, and so the voltage across resistor. So we will have UK, which is the voltage across the switch, will be equal to UG minus U coil. So UG equal 10 plus 500, since U coil equal minus 500, which is equal to minus E, so UG minus U coil will be equal to 510. So this voltage is considered high, and so it produces a spark across the terminals of the switch. Now calculate the magnetic energy stored in the coil at the steady state. As we know, the magnetic energy stored in the coil is equal to half Li squared. At the steady state, I equal I maximum equal to ampere, so the energy will be equal to half into L, which is equal to 1.2 times I maximum 2 squared equal 2.4 joule. Now, as a summary, the power distribution in the coil as follows: B total equal P lost plus P magnetic. P total equal I UAB, which is the total power received by the coil during the growth of the current. P lost equal Ri squared is the power lost by Joule effect in the resistor of the coil, and P magnetic equal Li di over dt is the magnetic power associated with the self-induction in the coil, and the expression of the magnetic energy stored in a coil, growth or decay, is W equal half Li squared. This is the end of part 4. Thank you for your listen.